Today we are going to see single sideband technique. In the previous lecture we have seen amplitude modulated signal where there are three components. One is the carrier itself and other two are the sidebands, lower and upper sidebands. Now if you look at the equation of the amplitude modulated signal, then it is as shown. VAM is equal to Vc sin omega Ct plus MVc by 2 cos of omega C minus omega Mt minus MVc by 2 cos of omega C plus omega Mt. This equation we have seen last time. In this equation the first term is carrier and the second and third terms are the sidebands. Now you can understand that the given equation, second equation, is the power equation of amplitude modulated wave, where the power in the amplitude modulated wave is carrier power into 1 plus m square by 2. If you think the case or the situation where the carrier is suppressed, look at this equation. In the equation of amplitude modulated wave, if Vc sin omega Ct is suppressed, then what will happen? There will be a large power saving. As you can see that if the modulation index is 1, then the total power in the modulated wave is 2/3 of amplitude modulated wave power. The carrier power in the amplitude modulated wave is 2/3 of total power of amplitude modulated wave. It means almost 66% of power is there in the carrier itself, which we are sending with the amplitude modulated wave. So this power can be saved if you suppress the carrier. So therefore a significant saving in the power requirement can be achieved by suppressing the carrier before transmission. This thought process led to the first variant of basic amplitude modulated wave termed as double sideband suppressed carrier technique. It means we are sending both sidebands but we are suppressing the carrier. We are not sending it. So here red colored question is there. Calculate the percentage of power saving in double sideband suppressed carrier amplitude modulated technique when modulation index is 1 and when modulation index is 0.5. So that is the assignment to you. Now total power in the double sideband suppressed carrier will, now carrier power is moving out. It is not there now. So it is just Pc into m square by 2. So Pc plus Pc into m square by 2, this was the power in the amplitude modulated wave. Now Pc is removed and Pc into m square by 2 is now the power in the double sideband suppressed carrier modulated wave. So calculate the power in the DSB SCAM when modulation index is 1 and when it is 0.5. For this you have to assume the carrier power. Say for example you can assume carrier power is 400 watt. Then what it will be for modulation index of 1? Then what it will be for modulation index of 0.5. Now in order to suppress the carrier, what we have to do? We have to just take the amplitude modulated wave and subtract Vc sin omega Ct from it. So the second equation is the equation of double sideband suppressed carrier. There you see only two sidebands and the carrier is not appearing in the equation. The bandwidth naturally of the double sideband suppressed carrier amplitude modulated wave is remain unchanged because only carrier is suppressed. Both sidebands are there and the upper sideband frequency is Fc plus Fm and lower sideband frequency is Fc minus Fm. So the difference between these two is 2 Fm and hence the bandwidth of the suppressed carrier signal is same as amplitude modulated wave without separation of the carrier. This is the frequency domain representation of double sideband suppressed carrier wave. This you will find familiar with the amplitude modulated frequency domain representation because it is the same diagram with the difference that the middle line of the carrier signal is missing here. Only two lines representing LSB and USB are there, and also time domain representation will be similar. Only thing is that carrier is missing, so you will find the two sidebands crossing or overlapping each other. These are the advantages of double sideband suppressed carrier technique. It provides 100% modulation efficiency. Now because in the AM wave there was not possible to provide 100% modulation efficiency, but it is possible over here. Due to suppression of carrier, great power saving is achieved, and hence from that point of view it is less costly technique. Double sideband suppressed carrier technique allows us to have a transmission that reduces overall power consumption rate, thereby ensuring stronger signal at the output. Of course, any advantage does come with the price. So the disadvantage of double sideband suppressed carrier modulation is it involves complex detection process. As you know, the suppression of the carrier is itself complex process. Again, when this signal reaches to the receiver, it is difficult to recover the signal at the receiver because carrier is missing. So you have to reinsert the carrier at the received signal, and then you have to recover the original signal. Hence this becomes expensive technique. The application of this double sideband suppressed carrier is that it is used in binary data systems, and wherever two channel stereo signals are to be used, this double sideband suppressed carrier are used in television and FM broadcasting. Now you will think how to suppress the carrier. So the technique or the circuit used is called as balanced modulator. This balanced modulator uses the nonlinear property of the resistive material. Some resistances are linear, as the passive components resistance which you are using in the laboratory, they are linear. But the resistive part of the active component like diode, transistor, they are non-linear resistances. There, if the currents are mixed or they are multiplied, then that mixing goes in the non-linear fashion. That non-linear output has many terms, in which one of the terms are sidebands. And if these two outputs, that is the upper FET output and lower FET output, if they are mixed, then they will suppress the carrier because the upper FET is getting the RF signal as it is, but the lower FET is getting AF signal with the phase shifted manner. So that creates the cancellation of RF signal as seen from the equation. So these are the equations of the output of the balanced modulator. Here you will see that the output equation VO has three terms. One is P into sine omega mt, other is Q into cos omega C minus omega mt, and the third is Q into cos omega C plus omega mt. So it is easy to understand that the first term is modulating signal itself, whose frequency is very less. It is almost 1000 times lesser than the sideband frequencies. So this signal can be easily removed by the proper tuning of the balanced modulator output circuit. And the remaining two terms are just sidebands, the lower sideband and the upper sideband. Hence, from the equation you will easily come to know that the carrier is suppressed. It is not present in the output. Now, if the carrier is suppressed, then whatever is the remaining is called double sideband suppressed carrier. But if you look at the equation and if you know the property of the sidebands, you will understand that both sidebands are identical. identical. It means the upper sideband, its amplitude is same as the lower sideband. Only thing is that there is a difference in the frequency. The frequency of the lower sideband is fc minus fm and that of upper sideband is fc plus fm. But the information is same. Information is basically in the instantaneous change in the amplitude, and that is same for the both sidebands. It is mvc by 2, right? So why not to suppress extra sidebands as well? If you replace it, if you suppress it, then it becomes single sideband technique, and this technique is called as single sideband suppressed carrier technique. The advantages are that again its bandwidth is reduced because it is now only FM, and the power also can be saved. The amount of noise present is less as the bandwidth is reduced, and loss of signal is also less because now it is bit complicated and coded sort of signal. So there is no loss of signal, or there is no sort of theft in the signal. It is most secured. The disadvantage of the single sideband modulation is that again naturally its generation is complicated and its reception, that is demodulation, is also complicated. Hence the cost and complexity is higher. There are the applications. It is used in air, land and maritime communications. It is used in radio and point-to-point communications. Again in telemetry, TV, radar systems and military communications. As far as the techniques of single sideband are concerned, there are 3 techniques. One is called as filter method. We know that the output of the balanced modulator has only 2 sidebands. Then simply you insert one filter. It is called as sideband suppression filter. The sideband which you want to remove, insert that particular corresponding sideband filter, then other sideband will be available at the output, and then that output can be easily transmitted using single sideband transmission technique. So this is one of the methods. It is filtering method. Crystal oscillator, in the last stage it is added in order to increase the frequency of the output single sideband. Another technique is called as phase shift method. Here 2 balance modulators are used. So upper balance modulator is getting carrier with the phase shifted and audio signal as it is, and lower balance modulator is getting carrier as it is but audio signal phase shifted. And then these 2 balance modulator produces both the sidebands, but if you mix them you will find that one sideband is getting removed because of their plus and minus sign, and the other sideband you are getting at the output. This is easily understood from this equation. So here at the third last equation you will see that VO is equal to V1 plus V2. V1 and V2 are the outputs of the balance modulators. If you add them, you are getting omega CT plus omega MT, that is the upper sideband you are getting, and plus 90 degrees there. That phase shift does not make any difference as far as the intelligence of the signal is concerned. So this is how one sideband can be reduced or suppressed. The third technique of single sideband is called as third method. The third name itself is coming because this is the third method. The earlier 2 methods were filter and phase shift method, but this method is third method. This also is same like phase shift method, but still there are certain additional blocks. You can see these blocks and you can study their equations, from which you will understand that the output of the third method contains only one sideband. The mathematical treatment can be easily seen from the books, but this method is obsolete and it is not used many times in the practical methods or practical applications. Another point in the single sideband is vestigial sideband. See, when one sideband is removed, the important portion of the other or required sideband also gets removed due to filtering method. Hence, it is necessary to send some part of the non-required sideband also with the required sideband. This method is called as vestigial sideband technique, and the application of this method is in TV broadcasting. This is the diagram of vestigial sideband technique. Here one sideband is getting transmitted, and the slope portion you will see that in the upper diagram the slope was not of higher or lower value. It was steep as far as the slope is concerned, but in the lower diagram the slope is lesser, so some portion of the unwanted sideband is also getting transmitted. Thus complete information of the wanted sideband is transmitted. The application of vestigial sideband is majorly in the TV broadcasting. This type of amplitude modulation is mainly used for TV broadcast worldwide. In this broadcast, it is essential to broadcast the information of video and audio concurrently. So here we end up our lecture of single sideband technique. You please go through the notes provided to you, and you can ask any doubt in the coming sessions. Thank you so much.